Hello everyone, thank you for tuning in. I'm Oana Balmau from the University of Sydney, and today I'm going to talk to you about redesigning storage systems for future workloads, hardware, and performance requirements. So I'm a computer systems researcher, and more precisely, I am doing storage systems research. So in the next 50 minutes or so, I'm going to try to convince you that the storage landscape is changing rapidly, and as a consequence, we need radical storage system redesign. When I say that the landscape is changing rapidly, I am mostly thinking of three main dimensions. First, we have new applications, then new hardware, and third, new performance requirements. I'm going to go through each of them. So, what do I mean by new applications? Have you ever considered what happened in an internet minute? So, in addition to the hundreds of hours of video that are being uploaded and read, the thousands of Internet of Things connections, and not even to mention the billions of impressions that are collected by most web services for analytics, a lot happens in just 60 seconds. Besides having to deal with these huge volumes of data, the way that we interact with the data is also changing rapidly. Let me illustrate this with an example. So, in the past, say around 10 years ago, a lot of the internet use was in the style of what we now have on Wikipedia. Web pages were mostly used to consult information and rarely updated. To get an idea, just the read-to-write ratio right now on Wikipedia is in the ballpark of 1,000 to 1. Now, of course, these kinds of workloads still exist, but they're far from being the majority. In the future, workloads will look very different. And let's take an example from the Internet of Things sphere, which is an exciting class of applications that is growing right now. The data circulation will no longer be one-sided, and in fact, in most scenarios, we will write almost as much as we are reading. For example, in IoT workloads, we'll read huge amounts of sensor data in order to perform controls or analytics. And on the right side, of course, the new sensor data is being continuously recorded. As I was saying, the size of the data that we're dealing with is also huge, in the order of zettabytes. So this data is also expected to grow exponentially in the coming years. And what this means for storage is that we will need to figure out a way to serve data efficiently from persistent storage because increasingly the working data set won't be able to fit in main memory. An additional challenge is that the nature of the data is also quite diverse. So I'm saying here that we're producing mostly unstructured data, and by unstructured I mean two things. First, the relationship within the data points are changing as the applications that need to use this data evolves. And second, the data has a wide variety of types and sizes, ranging from a few bytes that might store an integer to a few hundreds of megabytes to store a video. So we see that the more traditional relational database management systems aren't really built to cope with this amount of change. So how can we handle all of this unstructured data? Now, this is where my research comes in. I have been focusing on key value stores, which are the go-to systems for handling large unstructured data. Their structure is similar to a dictionary, which links a value to a key. The key is a small identifier, and the value could be anything from an integer to a picture or a video. Their API is simple. We have put, get, and scan operations to add data to the data store, retrieve data from the data store, and retrieve a range of values from the data store. These systems are widely used in industry and they run at huge scale. Some popular examples are Cassandra, RocksDB, or Redis. And just to give you an example of the scale, Apple probably runs the largest Cassandra cluster in the world with more than 75,000 nodes backing iCloud. And Nutanix, a company I have been collaborating with, uses RocksDB to handle metadata for thousands of clients with petabytes of storage capacity. Now that we have an idea of how the applications are changing, let's have a look at how the hardware is changing. Again, until around the past 10 years or so, the storage landscape looked quite simple. We had main memory, we had a hard disk, and maybe some tape for archival use. Now things look a lot different. Many new things are happening in storage hardware. There are two new layers between main memory and hard disks. We have SSDs and non-volatile memory. Also, on the archival storage space, there are very interesting developments with the glass and DNA mediums, and I've just visited the Microsoft research group in Cambridge who's looking at the Silica project, which is the glass storage. It's very exciting. However, today I'd like to share you something else. I'd like to tell you about some exciting things that are happening with SSDs. So, what's new with SSDs? First of all, they're much faster. So this plot shows a sketch of the bandwidth evolution for SSDs over the past 10 years. And today I'm going to focus on the 2018 SSD, which is the Intel Optane one. As we can see, the write bandwidth has been increasing by an order of magnitude. In addition to SSDs being much faster, they also have the very interesting property that now random accesses are almost as fast as sequential accesses. And this is a key property that will influence the design of key value stores for these new kinds of SSDs. However, before diving into that, I'd also like to tell you about the new performance requirements for storage systems. So, in storage systems, traditionally we care about throughput, and we still care about throughput. This means how many reads and writes we can do per second. The more the better, and also we want the throughput to be steady with no fluctuations. But now, as the amount of data that we are accessing from persistent storage is increasing, we also care about latency, which is the time that it takes to read or to write, and this time lower is better. Also, when we're talking about latency, we're very interested in what happens at the tail. So this is towards the high percentiles of the latency distributions. A typical example is the 99th percentile latency. So let me show you why this is important with a simple example that we all do on a regular basis, which is online shopping. So even to display a web page like this takes hundreds of requests to a key value store system to retrieve things such as ratings, pricing, or recommendations. So now, because it's often the case that applications access the data from persistent storage, a slow response from the storage system directly translates to a poor user experience and the difficulty to provide quality of service guarantees. For example, at Amazon, it's estimated that every 100 milliseconds of latency causes a 1% decrease in sales. So tail latency is very important. Now that I've given you a brief overview of the new applications, hardware, and performance requirements, let me tell you about my contributions in this field. First, I have been looking at the new applications. In this specific example, it was the metadata management in clusters. This work was done in collaboration with Nutanix in one of my internships there. So the problem we were looking at here was that the write amplification due to maintenance operations in the key value store had a huge impact on performance. So here, write amplification is a measure for key value stores that is saying how much data is written by the key value store compared to how much data is actually written by the application. So this metric can be up to 9 or 10 in write-intensive workloads like this metadata management. So this drastically impacts performance. So in Triad, I came up with a series of complementary techniques that are workload agnostic in order to decrease maintenance I/O and write amplification and increase client throughput. In principle, we use the hyperlog log-driven compaction, repurposing of the write-ahead log, and hot-cold key separation for skewed workloads. And the very nice thing about this project is that it's now used in production at Nutanix in their clusters. So just to give you a sense of the key result of this work, this plot shows the average throughput on the y-axis, so higher is better, and it compares Triad, which is in blue, with a series of state-of-the-art key value stores used in industry right now. We can see that these techniques to reduce write amplification yield up to an order of magnitude improvements in throughput in write-intensive workloads. In my second project, I looked at new hardware. In this case, I looked at servers with ample memory sizes in the orders of hundreds of gigabytes. And the problem here is that the state-of-the-art key-value stores, because of their in-memory structure, weren't capable to scale the throughput with the memory size if more memory was available to them. In fact, in some cases, the performance would even become worse with more memory. So to tackle this issue, in FlowDB, I devised a new type of data structure for the memory component of the key value stores. This is a two-level data structure, and in principle it has mostly O of 1 inserts while being highly concurrent for both reads and updates. As a consequence, I managed to obtain up to an order of magnitude increase in throughput under bursty write workloads. Again, to give you a taste of the key result, here we have a similar plot as the other one, this time showing FlowDB, which obtains order of magnitude improvements for write bursts. For my third contribution, I was saying that tail latency is also very important in storage systems in addition to throughput. So this is exactly what I have been looking at here, also in collaboration with Nutanix in another internship that I did with them. So in this work, we find that the I/O bandwidth sharing between key value store maintenance operations and client operations is causing negative interference. So I/O bandwidth was the bottleneck that was causing this interference, and in order to address this bottleneck, I introduced the new concept of I/O bandwidth scheduling in key value stores. So by using this scheduler, we managed to reduce the latency spikes and to obtain smooth performance. So to give you an idea of how bad these latency spikes were, they could go up to seconds in the conditions where average latency for these kinds of key value stores was in the order of a few microseconds. So how did we achieve this with the scheduler? The basic idea is that we opportunistically allocate I/O bandwidth for key value store maintenance operations while prioritizing the client work. Again, to show you a sample of the key result, this time in this plot we are looking at tail latency at the 99th percentile, so this time lower is better, and note the log scale on this plot. So here Silk is shown in blue, and the other systems are shown in orange, and we can see that Silk, because of this new idea of I/O bandwidth scheduling, is managing to obtain up to 3 orders of magnitude improvement in tail latency. So this is all that I'm going to say about the previous 3 contributions, because today I'd like to focus on VEL, which is a system that I designed to take advantage of the properties of new NVMe SSDs. So these are block-addressable devices. And the reason why I want to spend more time talking about this today is that it very nicely touches upon all of these 3 dimensions of change. So I'm looking at new applications, which are these write-intensive workloads that I was mentioning. The new hardware is this new Intel Optane drive. And in terms of new performance requirements, in VEL, we are looking at both the throughput and the tail latency. So how did this all start? One day we had received the new Intel Optane drives in the lab, and I was very excited. I wanted to run some of these key value store experiments and see how much better we can do. So I took one of the usual suspects, which is RocksDB, and I want to say that in this talk I'm going to use RocksDB as the running example, but similar behavior, I have noticed similar behavior on most of the state-of-the-art systems that I have tested with. So it's this is just one example. So what happened when I tried to run RocksDB on one of the standard benchmarks, which is a write-intensive, which was with a write-intensive workload, using this new drive? A rough estimation of the performance prediction was around this blue dashed line. However, the reality was quite different. it turns out that RocksDB has low and unstable throughput when it is running on top of this Intel Optane drive. So just to make things a bit more clear, I want to say that I have been using RocksDB throughout my work over the past years, and I have had the chance to work with the engineers at Facebook who are on the development team for RocksDB, and also with engineers of at Nutanix who are using the system every day. So we have tried together to adjust and tune the system so that, as much as we could, the performance of RocksDB wasn't due to bad tuning, but rather the more principled issue with the RocksDB's design. So let's dig a bit deeper into this result and see what's happening. So since this is a new drive and these types of key-value stores typically consume a lot of I/O bandwidth, as I was saying in the previous work, the I/O bandwidth was the bottleneck, I would have expected that RocksDB would run close to the maximum I/O bandwidth that's offered by the device. However, on average, RocksDB uses less than half the available I/O bandwidth for this device. And this next plot actually offers the key to the mystery. If we look at the RocksDB CPU utilization over time, we can see that it runs close to 100%. So the design of RocksDB isn't suitable for modern hardware because the system isn't capable to saturate the I/O bandwidth that comes with the device because it becomes CPU bound first. So all of this extra performance that we could get just by using the new storage device is wasted. And in order to understand why this happens, we need to go a bit into the internals of key-value stores. So here I'm going to explain to you how log structure merge key-value stores work. This applies to RocksDB, but also to lots of key-value stores that are designed for write-intensive workloads that are served from persistent storage. So this is a class of key-value stores that I'm talking about today. So these log structure merge key-value stores have two components. They have the memory component and the disk component. The memory component serves as a write buffer. So this is based on the assumption that writing directly to disk is rather slow, so we are going to buffer all of these writes in the write-intensive workload in memory. Now, when the memory buffer is full, it's getting written to disk, and as a result, we have a collection of sorted immutable files on disk. And by immutable, I mean that once the file is written to disk, we cannot modify it in place. So, to give you an example of how the writes are being absorbed by this key-value store. So when the memory component gets full, it's going to be replaced by a new empty write buffer, and the old one is written to disk in one large sequential write. Now, this is a very good idea for old drives because they are a lot more efficient for large sequential writes than for small random writes. So this process keeps happening, and the new files can keep being written, and if this continues, at some point we would end up with a number of these files on disk. Now, this isn't a great idea, obviously, because we would end up having lots of space amplification and also lots of duplicate data, which would lead to poor read performance. So we need an operation to merge these files. The merge operations in log structure merge key-value stores is actually a lot more complicated than what I'm showing you here, but for the purpose of this talk, it's enough to know that two or more files are being chosen from disk, read up into main memory, and being merged in main memory. So this is a similar operation to just a merge of two sorted files, but it's CPU intensive because in addition to the merge, we also need to create auxiliary data structures such as indexes or Bloom filters and other auxiliary structures. So When the merge is complete, the new file is written back to disk. Also, you need to imagine that this is just one merge that is going on, which is pretty CPU intensive on its own, but there can also be a lot of these parallel merges going on at the same time in the key value store, which puts even more of a burden on the CPU. So now we have the real key to the mystery. In fact, when we have a closer inspection of what's going on with RocksDB, showing this CPU utilization plot, actually RocksDB spends 60% of its time merging and creating these auxiliary indexes of the new files that are added to the disk structure. So, as I was saying, this applies to RocksDB, but not only. So they apply to a number of key value stores that are used for persistent storage, including some of my own. So the bottom line is that the main assumptions that these key value stores make about the hardware no longer hold. So the two main assumptions are, first, that I/O is the bottleneck, and second, that a long and sequential write is much better than short random writes. And of course, as we have seen, this is no longer the case for the new drives, which offer, first of all, very high bandwidth and random access, which is almost as good as sequential access. So some of the things that these existing key value stores are doing because they are making these assumptions about the hardware are that they're making a huge effort to ensure large sequential writes. And this usually takes the form of sorting, or making an effort to ensure that the data is sorted and can be accessed sequentially. A consequence of wanting to keep the data sorted is that a number of shared data structures are used, and in write-intensive workloads, this can create contention. And finally, again, as a consequence of the sorting, we have a number of maintenance operations, such as the merging or cleanup, which need to be done by the key value stores, and they can be very CPU expensive. So how should we redesign key value stores for fast drives? And if there's a thing that you want to remember from this talk, this is it. So the key idea in storage systems so far has always been to optimize for the device use. And this has led to a number of design decisions like disk scheduling, sophisticated disk space allocation, centralized caching, and so on. But today, you're not going to hear about any of that in this talk, because the basic paradigm has changed from optimizing disk I/O to optimizing CPU. And let me give you a brief example of what I mean when I say the CPU budget is tight. So this is an approximation done on our machine, which is running 4 cores, and it has one such Optane drive. So we have on average 500,000 IOPS per second peak IOPS. That means that we have one I/O every 8 microseconds. So if we want to run at full disk bandwidth, we need to fit the operations in this 8 microsecond budget. Now, if we want to run a key value store for write-intensive workloads, we would imagine that we need at least one write system call, which is around 4 microseconds. Also, we would need to access or look up some kind of data structure, which would also take around 1 microsecond roughly. Now, as you can see, this leaves very little time for the remaining key value store logic if we want to operate at full I/O bandwidth. So how should we do this? Now, Quell's design is for streamlined CPU use. So basically, everything that we found that the other key value stores were doing, which was expensive in terms of CPU cycles, Quell isn't doing. So Instead of expensive sorting, we have decided to keep data unsorted on disk, and this is only possible because of the properties of the new hardware, which allow efficient small random writes. Then we chose shared nothing design in order to avoid contention on shared data structures, and finally, we don't want any maintenance. Now, I'd like to give you a heads up that what comes next may seem simple, and that's the point. The contribution of this work is that the design must be simple, otherwise you cannot fit in the performance constraints. So, having warned you, let's proceed with looking at Quell's design in more detail. Now, the first principle is to keep data unsorted on disk. So, our disk layout was inspired by in-memory allocators. We maintain one file for each key value item size class. So, this makes adding new entries to the data store as follows. First, we need to find the appropriate file for the item size class, and then we just add the entry in the first free slot. No sorting required. However, we need a way to be able to retrieve the elements that we have written to the data store, and for this we need an index that lives in memory. Now, depending on the kinds of operations that we want to support for the data store, we can opt for a hash table index if we only require point queries, or if we want range scans, we will need a sorted index. So this is what we are using in Quell. We are indexing the keys by prefix, and each index entry contains a reference to the file and the reference to the position in the file where the item is located. So to give you an example, we have a key for which could look something like this. Then a prefix is taken, and we are storing the file reference in the index and the item position. The second principle in Quell's design is the shared nothing approach. Now, this is done through sharding, which is a static partitioning with n independent worker processes. In this simple example, n is 3, and we are using a simple function to shard the data across the 3 workers. Now, you might wonder, how about load imbalance? So this is an obvious question, and we found out the following. So at the level of the storage stack where Quell would reside while using this new kind of fast drive, the workloads will tend to be two of the following. Either they will look like a uniform workload, in which case it's no problem to have the sharding in this way, or they will have a very skewed profile, in which case the caches will take care of the skew. Everything in the middle, it turns out, while analyzing some of the production workloads at Nutanix, everything in the middle will get pushed down to the lower levels of the storage hierarchy, so that effectively we wouldn't see any skew in a system that is operating at this level of the stack. So the good news with this static partitioning is that each of the worker threads can have their own indexes and their own file structure. So this means that virtually no locking is necessary, and only minimal synchronization is needed to put together the results from the scans when the scan is done on all of the partitions. And this leads us to the final design principle in Quell, which is really more of a consequence of the two other design choices that we made. So the final design principle is no maintenance. Because each item is the items are unsorted on disk, and we are not making any efforts to maintain a structure, this allows every item to be persisted at their final location. So no moving or garbage collection is necessary. If an item is deleted, its spot will just be freed and it will be reused by a subsequent update. So that's it. We have virtually no maintenance in Quell. Now, just because the system looks simple doesn't mean that it was easy to implement. Actually, we had a number of challenges which all stem from the fact that it is difficult to have an efficient implementation at such high request rates. And even small inefficiencies can compound to have large delays. And I'd like to give you one such example, which is linked to the page cache implementation. So first of all, we have tried to use the operating system page cache, but it turned out to be a major bottleneck, and it wasn't in line with our shared nothing approach. Also here I should mention that the page cache is used in a slightly different way in Quell, so we are writing directly to disk, and the page cache is only used for reading. So we decided to implement the page cache from scratch because we couldn't rely on the operating system one, and we started looking at a number of data structures. We found a very promising one in our tests, a hash table which would give us a few microseconds per operation. However, what we didn't realize was that the worst case was really slow. So the worst case occurred when the hash table was getting close to capacity and needed to double in size, which would take in the order of tens of milliseconds. Now, at such request rates, this happens often enough to impact the tail latency. It would lead to backlogs of tens of thousands of operations, the I/O queues would get really large, and this would lead to tail latency spikes. Now, after we figured out where the problem was, we adapted our hash table growth strategy. So instead, we opted for a version of linear hashing inspired from an algorithm from the 1980s. Now, the point here is that the small inefficiencies can come from surprising places when you're operating at such high request rates. So now we've seen a bit of Quell's design. I hope you have a better idea of how it was built. And I'd like to go to the evaluation. So for today, I'm going to keep it brief, and I'm going to answer three main questions. First, how does Quell perform compared to the state-of-the-art key value stores? Second, does it actually achieve high throughput and low latency? And finally, and maybe the most interesting one, does Quell remove the CPU bottleneck? In terms of evaluation setup, I went with a simple, the standard industry benchmark YCSB, which was developed by Yahoo. In terms of hardware, we have one Optane drive, so it's the same machine that I gave in the example earlier, computing the CPU budget. And for the competition, I will be focusing on RocksDB, but having said that, the results that I show for RocksDB are actually representative for a number of state-of-the-art key value stores used in industry. Now, without further ado, let's look at the YCSB benchmark results. So this plot gives an overview of the entire YCSB benchmark. As you can see, it has a number of workloads ranging from write-dominated workloads to read-dominated workloads. We also have a scan-dominated workload. The average throughput is shown on the y-axis, so higher is better, and Quell is shown in blue. Now, we can see that across the board, Quell is dominating for point queries, and the performance is almost the same for the scan workloads, even if Quell doesn't sort the data on disk, which is quite remarkable. Now, there are many other things that are very interesting and we could say about these results, but for now, I will just focus on YCSB-A, which is a write-dominated workload that represents the modern workloads I was talking about earlier. So let's see how Quell performs in more detail. So maybe you remember this plot from earlier where RocksDB doesn't really rise to the expectation of what could be done with this new SSD. However, Quell manages to run close to the back of the envelope prediction and manages to saturate the disk bandwidth. This happens because Quell has a low contention and no maintenance operations. Next, if we look at tail latency for QVEL and BroxDB, so this plot shows a log scale of the tail latency on the y-axis, so lower is better. We can see that the tail latency in QVEL, because of these strategies for low overhead, is only a few milliseconds, while the latency in BroxDB can spike to the order of seconds because of these expensive maintenance operations that I was telling you about. And finally, let us look maybe the most interesting result for today. So this is these two plots are showing the I/O bandwidth use and the CPU use over time for QVEL and for RocksDB. So for RocksDB, maybe you remember from the beginning of the presentation that it runs at full CPU, and because of that, it doesn't manage to saturate the full I/O bandwidth. QVEL, on the contrary, it manages to run at full disk capacity while having low CPU utilization. Now, for us, this means two things. First of all, if the device would become even faster, it would mean that the performance of QVEL would continue to grow because it's not limited by the CPU. And second, because QVEL isn't CPU hungry, we could collocate other applications in the same machine with QVEL and run them, maybe using QVEL as a backend for storage. So, in summary, we have seen that QVEL outperforms the state-of-the-art key-value stores on NVMe SSDs. It provides high and stable throughput and low tail latency, and it manages to remove the CPU bottleneck. In QVEL, we managed to achieve this by being minimalist when it comes to spending CPU cycles in order to be able to maximize I/O bandwidth. And we achieve this through three main strategies. We have no sorting, no data structure sharing, and no maintenance. So now that the technical deep dive is over, I'd like to switch gears and tell you a bit about what the future holds. So there are three directions that I find very interesting for future research in the storage space. First, I want to design ways to efficiently support much more than what the simple key-value store API can do right now. As we know, even though key-value stores can back many applications, there are lots of others that require more complex operations and guarantees, like transaction semantics or snapshots or support for joins. A second direction I would like to explore is to design storage systems that address the needs of recommender systems. And I strongly believe that through better storage, we can produce much more meaningful recommendations. And finally, as I was mentioning in the very beginning of this talk, IoT is a massively growing field producing huge amounts of data. In fact, it's estimated that the amount of data produced by IoT alone in 2025 will be larger than the total amount of data that we will produce this year. So obviously, IoT is a very exciting space for storage research, both on the hot data management side and on the archival side, where we could possibly use new technologies such as glass storage. So this is a general idea of the broad directions I want to explore, but to end, I'd like to go into more concrete details about the first two directions, just to give you a glimpse of some things that I'm currently thinking about. So I showed you how to build an efficient key-value store with QVEL, but QVEL doesn't support more complex applications such as transactions. And this line of research fits very well with the big pictures that applications, hardware, and performance requirements are changing, and we need to respond through new storage system designs. So here at the application level, we have the key-value store API, which is too simple for certain applications, such as the ones in the financial space. And this is coupled with the emergence of the new NVMe SSDs that I was talking about, and also the persistent memory technologies. And finally, The performance requirement that we are posing here is that we want fast and high throughput transactions. So how can we support such efficient transactions? What I'm seeing now is that existing techniques, such as relying on a write-ahead log or heavy item versioning, creates bottlenecks on the new hardware. And broadly, my idea is to use insights from the transactional memory techniques and see how they could be adapted to create support for efficient transactions in key-value stores. More precisely, if we're being aware of the read and the write sets of the transactions, this coupled with the support for random accesses that is given by the new hardware, this would allow only a minimal lightweight versioning that would boost the performance of transactions in key-value stores. Now, the second direction that I find very interesting for building storage research, for building storage systems, are recommenders. So here, the problem I want to tackle is how often you get recommendations that you're actually interested in, or how often do you get recommendations that you're not interested in anymore. So, for example, and this might have happened to you as well, before embarking on this tour, well, now I'm at home, it got cut short, but I was looking to buy a travel yoga mat. And I bought it the first day where I looked online, but I kept getting recommendations for yoga mats the following week. Now this happens because the recommendations, the storage systems, the recommender systems are using stale data to perform the recommendations. And this is why I kept getting yoga mat suggestions for the following week. This is a practical problem that, as far as I know, nobody is addressing right now. And again, going to my framework, this boils down to having a performance requirement for a heavy read, modify, write workload. Now, I believe that through the new persistent memory and fast drive technologies, we can go towards achieving these real-time recommendations and supporting the read, modify, write workloads. And here, by real-time, I mean during the same browsing session. Now, the first question I want to answer in this space is towards the beginning of the pipeline, which pertains to data ingestion, cleanup, and just serving the data to the recommender system in the same browsing session for the user. So here I'm not even thinking about the recommender algorithm, but I'm just thinking about how to serve the data fast to the recommender. Now, the main idea that I want to look into is to create a system where the storage decides what data to run these compute-heavy operations on at any given time. And this I am hoping will speed up the read, modify, write operation, because right now the fact that you have to wait for the storage to respond is the bottleneck. So finally, just to mention, Pinterest is interested in this line of research for their social network, and we're currently collaborating on this project. So this concludes my talk. The main takeaway for today is that applications, hardware, and performance requirements are changing and will keep changing, and it's crucial that we build storage systems in a fundamentally different way in order to keep up. And finally, I would like to thank my advisors and all of my collaborators and the co-authors without whom the work that I presented today wouldn't have been possible. Now, thank you very much for your attention, and I would have loved to take your questions live, but please, I would really like to hear from you. Contact me either through my website or send me an email, and I would be happy to chat. Thank you very much.